Okay, so here we are. We are going to be starting statistics in bio today. This is chapter 17, and this comes actually right after you learn variation. Discontinuous and continuous variation, bar chart, bell curve. Now, whatever you learn here is going to be a little bit relevant to that, but actually it can be learned separately as well. You'll see why later on. Don't worry about it yet. Okay, so when I say stats and t-tests, which is this particular part, when I refer to stats, what I mean is there is standard deviation, standard error, and different math skills that are required that you need to know how to calculate. So this is a list of math skills required. I am not going to go through mean, median, mode, range in the quartile range. Many of you take maths, and therefore I expect you to know already. Now, if you have a problem with this, or struggle with it, let me know. I will help you out, okay? But it's quite easy, that part. So we're just gonna skip ahead to standard deviation, standard error, and later on the 95% confidence interval. Okay? Now, don't be afraid to spam the chat if you have any questions or just comments in general. I'm quite chill, just spam ahead, okay? Anyways, going on to standard deviation, yay! Now, the reason why I have to go through standard deviation, even though you already have learned it in maths, is because it's slightly different from the maths one. I'll tell you how later, but first I'm just going to give you an overview of what standard deviation is. Standard deviation is to show the spread of data around the mean in a sample that's normally distributed. So in essence, it is about what the shape of the bell curve is. So it is bell curve, but it could be flat or it could be like really tall, right? What does that mean? This means if it's flat, this means that data is spread out really a lot. Let me annotate that. Okay, data is spread out here. Whereas if it's really tall and like skinny, this is less spread out. This would really indicate the reliability of data. If it is more consistent and reliable and less scattered, you expect the standard deviation S to be a small value. So this one will have, this is less spread out. So this one will have a smaller S. So smaller standard deviation. Whereas if it's more spread out, then you expect it to have a large standard deviation. So large. So if it's more spread out, we deem the results to be less reliable. It means you have a larger spread of data instead of very close to the mean. Okay, so this is less reliable. Whereas if it's less spread out, it is more reliable. So other than indicating the reliability of data, we also use standard deviation, we'll see later, to calculate standard error and also to calculate the t-test value. So this is very important. Now, remember I said just now that it's different from what you learn in maths. Okay, now we're going to go through that. So this is the formula. You realize that it's different from maths. This is standard deviation equals, by the way. So S equals. Okay, first of all, what is different is the unknown use, the representative letter here. We use S, not, what do you call this? This is delta. Not sure. So we don't, here we use S. Okay, why is that? I'll tell you soon. And you also realize that it's not divided by N. Oh, thank you, sigma, small letter sigma. Thank you. This is big letter sigma, big S. Right. Anyways, you can see here that is not N, it is N minus 1. Why? Because in maths, you learn the standard deviation of the population, whereas in bio, we learn the standard deviation of a sample, and that's different. What do you mean by population sample? Okay, this is what we mean. Imagine this circle, Venn diagram, yeah? Imagine this circle represents all the entire population of, say, mice in the neighborhood, in the area, okay? Now, in bio, when we do experiments, we can't capture all the mice in the entire neighborhood, right? How to capture all the mice in the entire neighborhood? How would you know when you capture the last mice, whether it's really the last mouse. You don't know, right? And it's a lot of work, and it's pretty impossible to capture an entire population. Instead, we actually take a sample. So we take, of course, as many samples as we can, as feasible. Okay, but this is only a portion of the population. It is not really the entire population. It's just a part of the population. And therefore, the standard deviation is calculated using a slightly different formula to account for that little bit of error. Okay, sample would definitely not 100% the same as population. Okay, mean of the sample and mean of the population might be slightly different. Okay, the spread of data in the sample and spread of data in the population would be slightly different as well. So therefore, the formula is different. The way we represent it is also different. And this will become very important. Why? Because if you miss out this part, it will affect your standard error later and your t-test value. So yeah, you're going to get this right. Remember, it's n minus 1, not n. Okay, but other than that, it's the same. So this is meaningless if you don't have a sort of example to work on. So this will be the example we are going to work on today. So we are going to look at petal length of flowers in woodlands. I'm using a highlighter here. Woodlands, and then petal lengths of flowers in the garden. Okay, so two sets of data here. One in the woodlands, one in the garden. Okay. Now, the idea is this. We're going to figure out the null hypothesis. We're going to find the mean, a standard deviation for both sets of this data. Okay, what I'm going to do is I'm going to teach you how to do it manually, which you already know, but I want to make sure you know. And then we're going to learn how to use the easy way using the calculator. I've heard that you didn't learn it in maths, but some of you have already YouTubed it. So, well, either way, I'm going to teach you, and maybe it'll be useful in the future. Okay, anyways, after that, we're going to find out whether the two sets of data are significantly different by plotting a bar chart with error bars. And we're going to check that answer by conducting a t-test. Okay, so step by step, let's do null hypothesis first. Now, null hypothesis is quite standard. Okay, we're looking at two sets of data here. We're comparing them to each other. So, standard formula. There is no significant difference between petal length of flowers in the woodlands and petal lengths of flowers in the garden. You fill in the blanks. But same idea as before. Okay. All right, now we're going to find the mean, the standard deviation, and for both sets of this data. So mean, very easy. I have calculated it for you here. So you can see here, you sum up everything. So sum of x, sum of all of this, divided by 12, which is the n. Okay. Our next part is to calculate the standard deviation. I'm going to make this full screen first. Standard deviation. So we calculate it by filling up this table. So I know you have a rough paper somewhere near you that I've already asked you to prepare. So you can fill in this table. I will fill it in too. So I will suffer with you and you feel less bad about yourself. And then we'll compare answers and see what happens. I've already did this once with the S1. I'm pretty sure I'll screw it up again and have some mistakes somewhere. So you're gonna do it with me so that, you know, we can correct each other, you know? Make sure we are on the right track together. I'm gonna use green color because I feel like it. So this is the manual way of doing things. Oh, this one I can do by hand. Okay, it actually doesn't matter the sign really because you're gonna square it later. So I'm just not gonna include the signs and include a modulus in the top. It's just easier, okay? Don't judge. 3, no, 4. 2.77. Some of you are just like, haha, I won't do and Miss Bay won't know. Yeah, whatever, your loss. Did I screw it up? You know, when I teach stats, I'm actually quite nervous because, like, I feel when I teach bio, my mind is solely focused on bio, so it doesn't process maths very well. I'm not sure if that happens to you. It happens to me like all the time. I feel like pause and really make sure I'm doing the right thing. Is that right? So I modulus it so that I don't need to think about the values. Did I calculate that right? Let me know if I didn't. Then we go square it painfully, and there is so much room for error because if you get one value wrong, then you get the whole thing wrong, and then you have to go trace back where you're wrong at. So be careful. 0.2704. I think some of you chose to key in all straight, right? Well, you have a table here for a reason. You go fill it out. Okay. You realize that I'm writing all decimal places too because, well, I want it to be less error. I mean, I want a more accurate final result. So the final result can be in 3 sig fig or 2 decimal places. But I'm going to include all decimal places in the table. There's not too many anyway, just 4 decimal places. Quite manageable. Honestly, this process is long, arduous, and annoying, isn't it? You might be like, why didn't Miss May just teach us the shortcut? Because if you don't take the long way, then you won't appreciate the shortcut. Besides, you gotta learn both. Because they might fill up half the table and then ask you to complete the table. So you need to know how to do that. Or they can ask you to calculate from scratch. So, ta-da! Okay, let's sum all of them up. A bit lazy to key in all those numbers. We'll just square everything in one line. Oh no! I typed something wrong. Let's start again. So remember I said I forgot to bring my calculator home and it's like stuck in the office. That is true, but I did find this ancient calculator that was my brother's. My brother's like 10 years older than me, so this is at least 10 years older than my calculator, and you can't do a lot of stuff. It's very annoying, but you know, it's better than my phone. Yeah, don't mind me just monologuing while I work. The usual. Kinda used to it now. I bet you are too. So always 4 DP, I know. I just said just now, I said I wanted to make sure it's accurate, so I included all decimal points, but the final answer should be in 2 decimal points. Final answer, 2 DP or 3 sig fig. Whichever that looks better in that context. Okay, divide. Oh, don't forget to square. Root. Typo. Oh no, I must amend the slides again. So this is 12, n is 12, so that's divided by 11. Square root, you should get 2.638 or around 2.64. So 2dp or 3 sig fig. 2dp or 3 significant figures. Whichever that looks better, makes more sense. Okay, so I think I'm quite slow, although I do have the table drawn out. And I assume you're done now and frustrated with life. Did everyone get this answer, by the way? Anyone? No? Okay, your friend asks, Miss, usually mark scheme will give a range of value or just one answer for standard deviation? No, usually a range of values, say, I think plus minus 0.01. Yeah. So if you round off the previous values, then you end up with a very similar standard deviation, but slightly different. But it's okay, don't worry about it, okay? You'll be okay, you'll be fine. They are quite accepting. So yeah, this should be your answer. This is the mean, and this is standard deviation for woodlands. So we're just going to write it aside here. Woodlands. Should have done brown, yeah, what's brown for wood. I'm just gonna write some notes here so it's easier to view our data later on. Okay, and then the mean is 4.52, and our standard deviation is 2.64. Okay, now to the gardens. Let's calculate the gardens one. Let's change color to represent it. Red, I guess. Gardens. So in the gardens, there is 10. Okay, let me go back to the top. And this is the 10 flowers. This is the 10 petal lengths. And this time, we're going to use a calculator, and I'm going to teach you how. And there's no slide to tell you how to use it. So I'm just going to attempt to write the instructions here while teaching you how to use it. So take out your calculator. We are gonna do something. Let me reset it. Okay, so this should be our calculator. I assume that all of you use this like Chang'e new calculator. This calculator is the old one. This is the 570MS. This one works differently. I have to Google how because I forgot how. But this is the new version on the screen. Okay, and the instructions I give would be for this particular calculator. Okay, so the first thing you should do is to switch the calculator to statistics mode. So shift mode, okay, down, you see stats, okay, press 4. And if you see frequency, please press off. Okay, somehow my calculator is more glitchy than yours. No, my calculator is very glitchy for sure. So it might look different on my calculator slightly. But what happens on your calculator is you should see something that looks like this now. Okay. Right, because it's glitchy, I need to split screen like this. If not, it wouldn't work. I'm gonna write the directions here just in case you're a bit lost. So shift mode and then choose stat. And then make sure you off the frequency. We're not plotting a frequency table here of any sort, not like in maths. Okay, so we're gonna off. We never use it in bio. And you can see this screen, then you press la AC. Oh no, it crashed. It does this very often. I'm gonna repeat what I just did with you. Oh no, it's fine. All's good. Oh, I wonder whether it kept. Anyways, press shift next and then press 1 after you see. Okay, if you manage to go to stat, you will see stat on the top here. Okay, then shift 1 and then press 2 to select data. Okay, it should be an empty table. Mine has stuff in it because I forgot to clear the data. You know what? Let me clear while you figure it out. Clear the data, clear the data. Oops. Shift, clear. Memory? Yes. Oh no. Yes. Shift 1 data. It's still there. Whatever. Okay, let me write that down. Okay, then we're gonna key in our data. So how do we do that? We just fill in the table. This one we are doing flowers and garden. So I'm just gonna replace the data here. Okay, so I'm just gonna just click equals after each number. So there's 4 2.5s. 2.5, 2.5, 1. Oh no. I gotta clear my data. I'm just gonna reset the whole thing. And I hope it works. Okay, just ignore me. Mine's very glitchy. Follow the instructions that I wrote down there. Hey, now it's blank. Great. All right, 2 equals 5 equals. If you missed it, like you missed 1 2.5 or you missed one number, you can always add it at the end. The sequence doesn't really matter. And then if you type wrong, okay, make sure you check lah, okay? So 2.5, 1, 2.5, 2.5. Okay. Mine's fine, but if you find there's a mistake, just go like just press up and down. Okay, up and down, and then you can just replace that by just typing in the number and just press equal again. Okay, so that will work. So after that's done, you basically have the data already. Okay, if you have 10 data, but then you will see there's an 11 row. The 11 row is empty, so you can just leave it. It's fine. Just leave it alone. It's fine. Make sure you press enter after number 10. Then you just press AC. It's clear. They save your data already. Don't worry. Press AC. I just want to check. Is this in your notebook? Yes. Okay, good. All right, now we are ready to look for the mean and look for the what do you call the standard deviation. So what we're gonna do is we're gonna go shift 1 again, but this time we're gonna choose var, and we'll see this. Okay, shift 1, choose var. And you'll see these 4 symbols. N is the number of sample. X bar is obviously the mean. Can you see 2 fellas like this? So this fella, okay, small sigma, small letter sigma, is actually standard deviation of the population. Oh no, it crashed. And then this is standard deviation of the sample. Okay, we never use the population one. We always use the sample one. So please, 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 please press the right one. Okay, I hope they saved my data so I can do it again. Yes, they did. So shift 1 var, and then to find x bar mean equals. Yay. 4.52. I'm not gonna switch. I'm gonna write it down first because it's gonna crash. Okay, done. So try again. Var. Let's find the standard deviation of sample. So SX, not the sigma. Let's go. Number 4 equals 263. 8. Is that right? Did I do something wrong? That was not the number I got just now. That does not look right. Let's try again. Let's check my data again. It reverted. Told you it's glitchy. Right, you can press buttons and figure it out. You can use it to check the the Woodlands data as well that you calculated manually, you should arrive at the same answer. While I fiddle around this to find out. To make sure the data is accurate. Okay. Please work, calculator. Don't crash, calculator. Come on. 2.35. That looks more decent. Yeah, that makes more sense now. 2.35 and 0.2529. What was it just now? Forgot already. Shucks. I think it's 2 point something. A good thing about this, it's already saved data, so you can always go back 2.35. Don't need to key in again. Yay, so easy, right? Don't need to go through the pain of squaring each one, summing all of them together. Oh, minus 1 by 1, square 1 by 1, and then plus it all together. It's just a pain. Please check answers like this. Okay. Depending on the question, they may ask you to fill in the table, then you have to do manually. If they don't, you actually can use this way. It's fine. Now, I want to show you something else. Let's say you want to show working, right? And you don't want to calculate mean manually like this. So you can go Shift 1, and you can go to sum, and you actually can find the sum of x squared and sum of x here. Wonderful things. So you can do that as well. Okay, again, you can, like I said just now, just in case you didn't catch it, you can use this to verify these answers here. So just renew the data again. So Shift 1, data, and then you key in the Woodlands one to this to check your data. 491.75, 372, 3, 6, 8, 1.5, 6.5. Oh, I did a mistake there. Always check back your data. Always check back your data. Always double check. Especially with stats, because you know the error does affect your other calculations later. Let's check our mean. That's 4.52, accurate. And then there is SX, which is 2.638. Yay! So that's correct. So now that's how you use the calculator to find these values. Yay! Alright, so that's the calculator lesson over. Okay, so the instructions are already in the OneNote. Okay, so these are our values here. Now, what do we do with these values, and what can we say about these values? We can say a few things. We can say, well, Woodlands got 12 samples, Gardens got 9. Okay, mean-wise, Woodlands is more than Gardens in average. But let's look at standard deviation and what we can tell about it. Okay, we can tell that, hey, the Woodlands have a larger value of standard deviation, so this is less reliable. This here smaller value, this is more reliable. This data set is more reliable. Why? Because again, the standard deviation shows you the spread around the mean, the spread of values around the mean. See here? So, and you can see here in the data even, you can see the garden is like consistently 2.5. It's very, like the range is very narrow. The minimum is 1, the maximum is 2. Maximum is 3. It's like a very narrow range. All of them are very close to the mean, which is 2.35. However, in the Woodlands data, you can see that the minimum is 1.5, but the maximum is 9. And this is a very large range. It's spread over Yeah, it was very spread out. So you expect woodlands to have a higher standard deviation, definitely. Just by looking at data, you can see how it could be, whether it's bigger or smaller standard deviation. And this is also a way to check your answers lah. So if you realize that your standard deviation, this one is smaller than that one, then you are pretty sure that something is definitely wrong. You should recalculate and check your answers again. Okay, so that is standard deviation. Now we're going to move on to standard error. Now, in standard deviation, as I said, is the spread of data around the mean. Okay, so this graph here, and we only look for the sample standard deviation, which has a different equation from the population standard deviation. But now let's look at the standard error. The standard error tells us how close the mean of the sample calculated is from the true mean of the population. What does this mean? Again, back to this Venn diagram right here. Again, I'm telling you that usually in a bio experiment, we would only look at the sample. We only look at a certain sample of the population. We don't expect to capture the entire population. That's ridiculous. And you would expect the population to have a mean and the sample to have another mean. Okay, but these two means might not be the same, might be different. So how to calculate how close or how far this is? And the answer is standard error, which is also an equation. Okay, and it basically tests for the reliability of the mean. And later on, we use it to put error bars on graph as well. Okay, but the idea is the reliability of the mean. If it is a small value, just like standard deviation, it shows that the sample mean is close to the actual mean and the mean is more reliable. So the smaller the value, the better. Standard error is always between 0 and 1. So if your value is above 1 or below 0, a negative number, then you definitely know something is wrong. It's always between 0 and 1. So let's calculate the standard error here based on this little equation here. Standard error equals to standard deviation over square root of n. So let's do it. So this one would be 2.64 divided by square root of 12, which equals to, oh wait, it's my phone. That's my calculator. There, found it. 2.64, oops, 2.64 divided by square root of 12 is 0.762. Okay, it looks nicer in three significant figures, this one. But that's around, this is acceptable too. 2 decimal points is fine. Right, next one. This one would be, I hope you're calculating too, 0.529 divided by square root of 10 is equals to 0.167, which is around 0.17. Okay, so we can see the standard errors here for the woodlands and the garden. Okay, and what can we say again? We can say again that, look, this standard error is smaller. SM is smaller, and therefore mean is more reliable. In the standard deviation, we're talking about the data set, the entire data set, but in standard error, we're only talking about the mean, not the entire data set, just the mean. Okay, but obviously if your data is reliable, then your mean is more reliable as well, in general. So that's standard error. Anyone has any more questions so far? Everyone okay? So again, the error value is between 0 and 1. Is ours between 0 and 1? Yep. So that's correct. That's to be expected. I did type it down. Okay, now with this standard error, we can plot a bar chart with error bars. We need the standard error to plot a bar chart with error bars. Now I'm just going to skip ahead and talk about the bar chart first. So bar charts, we look something like this. Okay, usually we don't show all, Woodland's number is 12, right? We don't show all 12 data or 10 pieces of data. We usually take the mean and then we show the mean in the data, right? Because this is more simplified, it looks nicer and cleaner graph, it communicates the message better. Now the next thing we want on it is error bars. Now what determines error bars? Now actually in scientific papers and out there, there could be a lot of different things that influence the error bar size, but in A2 bio, in your syllabus, is always going to be these factors. It's always going to be this value only. Okay, this is only applicable in A2 bio. Outside, it might be different. Okay, here, what you're plotting here is your mean value, right? These error bars is actually plus minus 2 SM. So 2 standard error. This one is also 2 standard error. So what is this point here? This point is the mean plus 2 standard error. And this point here is actually the mean minus 2 standard error. So we really, the error bars, okay, in general, is actually mean plus minus 2 standard error. Okay, same here. Okay, the standard error is smaller, so the bar is smaller. Same thing here. They just use the standard error for gardens instead. So you can see here that the 2 standard error is smaller. So like if the woodland is smaller, then gardens is smaller lah. Yeah. This one I plot using Excel. Okay, using Excel very easy, but of course in the exam you are required to use manual methods, aka calculate and draw line yourself. So the question is really, okay, I get you, that's quite easy, but why 2 standard error? Like, what does it mean exactly? No one asked this, but I'm going to answer it anyway. So basically, error bars are upper and lower limits of a 95% confidence interval. Okay, so that's not very important. I mean, that doesn't, it's important to understand, but it's sort of abstract a little bit. I'll show you the graph. Okay, so when we say 95% confidence interval, this is also in sort of reference to the p equals to 0.05, but like the inverse, you know, instead of looking at the 5%, we're looking at the 95%. So in a bell curve, we are basically, by taking mean plus minus 2 SM, we are looking at the lower limit here and the upper limit here. Okay, the 5% or 2.5 at each side, we sort of like ignore. So we consider this is like the limits lah. Okay, why? Because here very little so it's negligible, so we don't care. We assume it occurs by chance. And we look at the 95%. 95% of the data. So this lower limit, okay, this is the mean right? So this lower limit is actually mean minus 2 standard error, and this upper limit is actually mean plus 2 standard error. So you can expect if the distribution is quite spread out, so standard deviation is high, data is spread out, then you expect this error bar to be bigger. Whereas if your standard error and standard deviation is smaller, then you expect this error bar to be smaller. That makes sense, right? So data more spread out, then your error bar is bigger. Your data is more consistent, reliable, then your error bar will be smaller. Makes sense. Now, you can see here that it says 1.92. That is somewhat equivalent to 2, and that's what we use for bio. A2 bio, that. So you can continue to ask me questions of why 2 standard error, but honestly, I can't answer you. People learn this in a maths degree. I didn't do a maths degree. People learn how to prove why upper and lower limits is 2 standard error. And I guess if you want to find out, you can read Wikipedia, but I don't understand the page either. So good luck. Okay, but for now, for A2 bio's sake, all you need to know, okay, you don't even need to know this is just like background knowledge. All you need to know is error bars is mean plus minus 2 error bar. Okay, so what does it mean and how does it show whether the result is significantly different or significantly not different? And the idea is if it overlaps, this means it's not significantly different and null hypothesis is accepted. If it is not overlapping, so this is not overlapping, then this is significant, non-overlap. So significant difference. Ada. This one got overlap. Okay, what is overlap? Maybe you cannot imagine. Anything that overlaps is overlapping. So even if there's a little bit overlap, this is overlap. Okay, so all these error bars, they all overlap. So all of these, no significant difference. They all overlap. Okay, however, this is not final. Like this is just the first step. This is like the litmus test. You know, you're sort of predicting whether it's significant or not significant. To be sure, we need to double check the t-test, which is a much accurate way of figuring out whether it's significantly different or not different. So we're going to do the t-test, but I know your brain's a bit fried. So I'm going to give you 5 minutes. We're going to start at 2:50. And the reason being, if we start earlier, we can finish earlier. It's not very, we're almost done. Like, we'll be done. So your friend asked, right before we have a break, your friend asked, so smaller SM means the mean is closer to the mean of the flower population in the garden. That's right. So the mean, sample mean is closer to the population mean. Okay, with that, let's have a 5-minute break. 2:50. Come back 2:50. And we'll finish quite quickly. Please spam chat with questions. Don't worry about it. Okay, I'm just going to leave this here for you to process. Hello, I'm back. So it's 2:50 and let's continue with the last part, which is t-test. So last part, t-test, yeah, is okay one, it's not too bad. It's just the formula, and the formula is given and you just need to know how to use it. And then you just need to read the table, but it's the same as chi-square. Okay, it's very, very similar to chi-square, just that the formula is different and some concepts are different, some requirements are different. So let me point it out to you, okay, as we go along. So here we go. Students t-test. There's many types, but this is a student's version, the easiest one. So t-tests are to test whether data from two samples are significantly different. Now this is different from chi-square. So if you remember chi-square, you're also testing if for significant difference, but you are testing between observed and expected. So usually you only are given observed and expected, you sort of use a ratio of some kind. Yeah, so it's either all equal or you follow a 9:3:1 ratio or something along those lines lah, right? You're only given one set of data, and then the other one you sort of use, this is given, this is you decide, you calculate. But here there's two sets of data given, two samples, like woodlands and gardens. So yeah, it's different. Also, in chi-square, they're using discontinuous data. That's why it's only for breeding experiments and ecological samples, because this is one organism, two organism, there's no 1.5 organism. Okay. However, in t-test, it's continuous data. So as we saw just now in petal flowers, there's 1.5, 2.5 mm. There's intermediates in between those data. Okay, so these are called continuous data. The data should be normally distributed vaguely. Okay, the two standard deviations are approximately the same, and two samples have less than 30 value each. So let's look at our data here and figure out whether our data meets those requirements. So this is our data here. So is it continuous? We have established that yes, there's 1.75, 2.5. It's not discrete. There's always intermediates. Okay, it's not categories. This is like quantitative data. Is it bell curve? Yes, it is. So you can see here, it's very obvious in this particular one. A lot of them are 2.5. And if you put it on like a little graph, you'll see that you can sort of make out the bell curve. It's not very obvious, but you can sort of find a little trend. Is it less than 30 samples each? Yeah, one got 12, one got 10. That's definitely less than 30. Is the standard deviation the same? Okay, around the same. And the answer is, yeah, pretty much the same. Why? Because, you know, standard deviation can get up to double-digit one. Okay, standard deviation can be quite big, but this is only like 2 difference. So it's okay. It's still quite reasonably, approximately the same. It is not too bad. Okay, so our data does meet all these requirements. And, okay, just for convenience sake, I'm going to copy paste what we have calculated so far here down there so that we can calculate the t-test value. Circle, 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 circle. Whee. Copy. Scroll back down. So we don't keep scrolling up and down. Okay. So we're going to do this and we're going to calculate the t-test value using the data we have. Now we don't need standard error, we only need the mean, the n, and the standard deviation. So S1 obviously is for one set of data, and S2 is for the next set of data. So I can just add it here, honestly. N1, SM1, SM1, and this is N2, just to differentiate them, yeah? Okay, calculate the t-test value. I'm going to do it with you, but you should try it as well. Don't confuse with the modulus with 1. There's a modulus. Draw longer. I just fail at writing. Square. I'm sorry, I covered the formula for you. Oh, no. Wrong value. 2.64 lah. Square. No, just 12. Don't forget to square your set deviation. Okay, type calculator. Remember to bracket. If you don't bracket, then you might end up something weird. Also remember to modulus. If not, you end up with a negative number. It should always be positive. 2.64 squared divided by... I will talk to myself now. So I think you should get, I don't know why I pressed the calculator because I already calculated it beforehand. You should get 2.781. 2.78 equals to 2 dp. Did everyone get the same number? Tell me if you get different number, okay? It means I calculate wrong somewhere. Okay, just want to say again, you're using standard deviation, not standard error. So I'm just gonna erase this. Less confusing. No standard error here. Standard deviation only. Standard error for error bar. Okay, thank you, Justin. Okay, so here you find the t-test value at 2.78. So how do you calculate the difference? How do you see it? You look at a table. So what do we need? Well, we need our t-test value. And we need our degree of freedom. You can see here, this is different from chi-square. In chi-square test, you only have one set of data, and then you find the expected yourself, remember? And then the degree of freedom is calculated by degree of freedom is calculated by number of categories minus 1. Category minus 1. But this time you don't have categories. You have number of samples for each data. So each one minus 1. So n1 minus 1 plus n2 minus 1. That is the formula. Okay, if you rearrange this, it will become n1 plus n2 minus 2. I feel like n1 minus 1 and n2 minus 1 makes sense the most. But in this case, either way you calculate, it is 20. Degree of freedom is 20. And that's very important. Now we're going to look at the critical value and the table. So always the cutoff point is p equals to 0.05. Okay, again, the degree of freedom is calculated by n1 minus 1, n2 minus 1, plus n2 minus 1. And in this case, it's 20. And the critical value here is 2.09. Now, there's a typo here. The t value we've calculated so far is 2.78. So where does our value lie on this line here? The value lies between this critical value and this critical value right here. I'm going to use red. 2.75. 75. 78. 78. Oops. 2.78. So what have we found so far? We have found that our t value is bigger than the critical value at P equals to 0.05 level. But it's also bigger than the critical value at P equals to 0.025. So it's bigger than both of it. So what level is it significant at? It's between these two, right? So we can say the level which this data is significant at is between P 0.001 and P 0.025. It's significant at this level. Now, obviously, the point here is that it's significant. So, how do you write it in other words? Okay, let's scroll down. If the t-test value is higher than the data in the table, the two data sets are significantly different. At what level? At this one is at this level. Okay, we can reject the null hypothesis then. Null hypothesis says that it is no significant difference. Obviously, that is wrong. And the differences are not due to random error or chance. Does it sound familiar? It should sound familiar. It's the same as chi-square test, just that now we're talking about t value, not the chi-square value. Same idea. The question might be, Miss, is this the same for all the stats tests? Well, for all the stats tests we learn, not out there, but when the ones that we learn, as long as it's higher than the value of the table, it's significantly different. Okay, always higher than the value in the table means significantly different. Okay, realize that this table here is not the same as the chi-square table. It looks the same, but the numbers are all different. So make sure you know what table you're looking at. Usually, they will give you the right table. You don't need to choose which table to see. And then, of course, the reverse of this explanation is true as well. So if the t-value is lower than the value in the table, aka the critical value, this means that the data is not significantly different and you should accept the null hypothesis. Any differences are due to chance or random error. In this case, we can conclude, in context of our petal length thing, we can conclude that here, the woodlands, petal length of flowers in the woodlands are significantly different from the gardens. Okay, realize that the t-test, as well as chi-square test, actually doesn't tell you if it's significantly larger or significantly smaller number-wise. Okay, it doesn't tell you it's more or less. It just tells you it's different. So how do you tell that which one is bigger or lesser? Here lah, the mean. Look at the mean. So you can see here that the mean is larger and it's significantly different. So this means that woodlands, petal length of flowers in the woodlands is significantly larger, longer than the flowers in the garden. Woodlands have bigger flowers, significantly, essentially. Okay, got that? So let's do one more example. Maybe you get an idea. Now the next example is actually a past year. I really don't remember from where, which I think I have to Google. But this is a past year, and this tells you the colorimeter measurements made on 10 samples of each of the 4 types of leaf. And you can see how it's shown to you here. There's 4 different leaves. They give you the mean absorbance. So this is already the mean. This is already X bar. And plus minus standard deviation, S. They show you already. So yeah, realize that it is standard deviation. And then they tell you, conduct a t-test to determine significance of difference between the mean absorbance of ivy and geranium. Not everything, just between 2. Data sets, t-test is only to compare between 2 data sets, not more. So, show the t-value is this. So this is such a nice question, honestly. They calculated the mean for you. They calculate the standard deviation for you. They tell you, oh sorry, I forgot to read the top, right? They say there's 10 samples of each, means n equals to 10 each. So nice. They tell you all the information. They even tell you the t-test value. They will always give you the formula. All you need to do is to prove it, to show the working, and to type in your calculator to show that you know how to do stuff. So yeah, let's try it. You should try your own calculator. I'm just gonna write stuff here. So again, it's between ivy and geranium only. Reading the question is very important. If not, you wouldn't have figured that out, and you wouldn't know that the number of samples is 10 each if you didn't read the question properly. Always read the question properly. If not, you might do careless mistakes like you did in your test. So many careless mistakes, I tell you, in the test. Oh, press wrong button. Don't forget to modulus the top. I pressed something wrong. Who else is like me? Always press wrong things. And then fail at typing. Okay, let's try again from scratch. I keep pressing the wrong button so the square root doesn't cover the whole thing. I'm just going to calculate each one individually and then put a square root over it after. Hey, you're right. My bad. Careless mistake. Standard deviation, not mean. Well, I'm going to start from scratch again. Hope you're not like me. That looks better. Yeah, that looks a lot better. Finally typed it right. Don't forget the modulus. So it should be this, okay, which is around this 2 dp. Okay, so I'm assuming you are done here. Hey, they say to use this, right? So never mind. I already shown it. So it's around 0.99 or 0.877. They gave you what to show, so perfect. If you want, you can actually show them the working and a few more steps. That is fine as well. Okay. Actually, it's probably a good idea to show all working, sometimes for marks. Anyways, moving on. What we're going to do? Oh, we're going to calculate the degree of freedom before we look at the table. So degree of freedom D, okay, just so I don't confuse you, D of F. Degree of freedom is n1 minus 1 plus n2 minus 2. I find that this makes a lot of sense. Minus 1, sorry. So equals to 18. Okay, because it's 10 each, so 9 plus 9. So now we can look at the table. Yeah. So let's look at always at the P equals to 0.05 level. Degree of freedom is 18. a critical value is 2.10. You can see here that our t value is smaller than our critical value. And this means it is not significantly different. And this means that, hey, we have to accept our null hypothesis. Our null hypothesis is true. And this also means that any difference are due to chance. I think. So scroll back up. This IV and geranium, no difference when it comes to current meter measurements, whatever that means. Ta-da. And that's done quite easy, right? I feel like stats is like it looks complicated. The language sounds fancy, but once you get it, you don't. It's very easy to solve. It's very, very easy to answer. They even give you the formulas. They're very nice in bio when it comes to maths. Because in the UK, some people who take bio do not take maths. They're not very strong at maths either in general. So yeah, they're very nice. So it's okay. It's not too bad. Yeah. So anyways, this is one past year. There's two examples. Of course, you need to do more on your own in order to get an idea. So what's going to happen after this class is I'm going to assign you work. Yay! Well, you won't get better if you don't do enough work. So I'm going to give you three different a compilation of a few questions. Cannot three whole papers. I'm going to show you the paper. Hang on. Opening. Where did I put it? There it is. So this is the paper. There's only 9 pages. Mostly they are pictures and really big anyway. There is one planning question. I felt like I needed you to learn how to plan this particular question. Okay, and the rest is like to do with error bars, set deviation, and whatnot. Okay, and we will have a live but optional class in order to discuss this. So whoever who needs, you feel like you really struggle, please come. If you feel like you only struggle with one question or 2 questions, I feel like maybe it's more worth it to actually watch the pre-recording and skip the question you want instead. Okay, other than this, actually, these are only a few questions. Actually, there's only 2 t-test questions here. One, they give you the formula and everything, and so nice to you. They even like write the equation halfway for you. Like, what in the world? Anyways, they do this. Okay, there's only one question. Then another one is more of writing, not so much of calculating. And if you don't want to do more questions, there's plenty of past years on t-tests. So to find those past years, just a reminder, I have it for you. Okay, if you go to your slides channel, and then you go to your files tab, there is something called paper 5, past year analysis. It's a PDF and a little table here telling you what year come out what. Okay, not for you to predict, it's to find the past year. So you can look at all these different places to get t-test practice. Now, a t-test comes out very often, but it's not because it comes out often in general, because the syllabus changed. Last time, in the syllabus only got t-test and chi-square, so they always come out. And you realize in the recent past years, there are many more varieties of tests and statistics things you need to know, and therefore, as in the recent years, more variety has come out. So I'm just saying, t-tests, yes, it is. There's a lot of practice out there, so good for you, but it is not the only thing that will come out. So please don't think that t-test is a popular question and you will only study t-tests. That would be a huge mistake. Don't say I didn't tell you. Okay, what else? Right, so I think we're done here, honestly. The rest of this week is pre-recorded. Okay, so yay to you. Okay, and honestly, it's quite a light week. Next week, there's one more video to finish the chapter. Just a reminder that tomorrow, 3 to 5 o'clock, I did post an announcement. Tomorrow, 3 to 5 o'clock, there's a test discussion. This is optional and will be recorded. I will release the results later on. I haven't finished marking every single person, but it will be done by this time on Wednesday and it will be out. Please do not discuss the questions in big groups yet, maybe like with friends you know already did the test, because there are 1 or 2 fellows who have not done the test. So don't make this difficult for everyone else. Okay, so that's it, I guess. Right after this class, I will assign you work. You will have the entire week to do it. We will have a live discussion that is optional as well next Wednesday, 3 to 5. Now this slot is going to be the slot where I put all the live and optional classes because well, all 3 of my classes are free during that time. So yeah, that's the idea. Now all of them are recorded, so you can skip, you can wait till the pre-recording's out and then skip to the timestamp needed. Nowadays, when you record like this recording, it will go into the general tab. Like I'll show you. Now you go into a general tab recordings, and I really hate that. I will always upload it back to stream. So don't worry, recordings will all be still in stream, all in those channels that I have created. That are very, very organized. I'm very, very happy with the system. Okay, so just last question before I end, I guess. Your friend asked, Charles can explain for first example why the significant difference is in 0.01. Okay, so for you're referring to this particular example. This is not the significant difference in this, but is significant at this level. Excuse me. So usually if it's bigger than critical value only, so if the value is just in between this, let's put it as x, it's in between this, then we say it's critical. This number is significant at this level, or sometimes you even put p less than 0.05 level. Why less than? Because if you read the numbers, they're all decreasing this way. So if you're here, that means you're less than 0.05. Okay. But this number here is in between our current number. It is between this probability and this probability. So it's no longer just significant at this level, it's significant at this level. So your phrasing is literally the data is significant at this entire thing level. You're showing them that your t value is in between these 2 critical values by saying that. I hope that answers your question. So yeah, that's the idea here. With that, I think we're done. If you have any more questions. Yeah. All right. Nigel asks, how close must the standard deviations be between 2 samples in order to use the t-test? It's quite subjective. I feel like maximum also like 2. Like usually the ones they give you in the questions are like super close. Like this and this are very, very close. They won't screw with you. Like they will give you 2 samples that have a very close standard deviation to begin with. They will never give you one that has a very, very different standard deviation and it's impossible to do. They will give you something that's possible to do, and they will give you the equation, and sometimes they even write the equation halfway for you. They are very, very, very nice, and this is why you should learn stats properly and use it to score paper 5. Because paper 4 is 100 marks and it's all words, right? Paper 5 got calculation, got this and that. I mean, it's kind of easier, I feel. Oh, and genetic diagrams. Easy places to score. So yeah, that's pretty much it. I'll see you guys tomorrow if you're coming. If not, next week. Or through a video. Oh wait, one more question. Means then they will give us the test to use, right? They won't ask us to choose the test to use. No, it depends. Sometimes they will give you all the data and then they ask what test to use. They might. Okay, but then they won't ask you to calculate. Because if they did, then they will be giving away their own answer. If you get what I mean. So they ask you to choose a test to use, they won't ask you to calculate because no formula will be given to, and they won't spoil their own, they won't give you spoilers. Okay, cool. Yeah, that's it. See you. Have a good day. Bye. Okay, you can continue asking questions in the chat. I'm still around. I just want to stop recording.